Have you ever wondered what it takes to create stunning or just any visuals in games and put them onto your screen? No? Well then, why did you click this? The whole process is actually quite complex, so today I will cover the basics in a rookie-friendly form. Let's go really quickly through what we have in menu today. I will help you understand what it takes to recreate 3D world of your favorite games on your flat screen by showing you what kind of work 3D artists and level artists have to do to create beautiful scenes that will not work slowly on PC or consoles. I will later go through what has to happen on a programming side, including, of course, graphics rendering pipeline overview. I will also mention what else happens during each frame of a game. Hopefully, it will all come together for you beautifully and you will have a better understanding how your favorite games are made. So, there are many things that need to be done in order to make a game and show it onto a screen. You need the code holding the whole logic for your game, whatever type of game that might be, but you also need assets, namely 3D or 2D models, textures and materials, which are technically code as well. There are obviously things like sounds and UI, but I will ignore them for now. Whatever happens in-game happens, usually, in real time, so if you click W and move your mouse around, you expect something to happen on the screen at that moment, not after 5 minutes. And this is what differentiates games from, for example, animated movies. Creating images on a screen has to be fast and precise, as you don't have 3 months to render your fully ray-traced animation created in Blender, Maya or wherever. This also means that every asset and every piece of code you put in the game has to be optimized in order to have a smooth experience, without lagging image or blurred assets. But what does optimized mean for 3D models? If you ever used any 3D modeling software, you might already know that each model is built from points connected together and filled in with triangles. Well, in 3D modeling software this can be any shape, really, but in games those are always triangles. The more points, the smoother and more detailed the model is, but it's also much heavier to present on a screen in real-time application, like a game. So you need to find balance between as few points as possible while keeping the visuals as appealing as they need to be. This is done through, among other things, textures, which are basically images that you glue to the model, or using more technical name, UV mapped to the model. Okay, maybe not that image. Yes, much better. Textures, so those images, also shouldn't be too big as it will cost a lot of memory, but they also shouldn't be too small as the model will appear blurred. There are a few types of textures that can be applied to the model. Most obvious is color, but there are also many other types like roughness, for example, which is black and white texture describing how the object interacts with the light. If you're interested in what magic you can do with various texture types and what texture types there are, let me know in comments. The real game changer, however, is normal texture, as it can fake the amount of detail that model has. Obviously, it can be done better than this. You know, it is this bluish texture that describes where the light should be reflected and where it should create shadows. With this texture, even low poly models can look incredibly detailed, which allows game creators to put lots and lots of various models in the game rather than just 2 or 3. Of course, my attempt on creating such details are, well, I am not a 3D artist, okay? So now we have models, we have textures, yeah. We probably have an engine doing all the heavy lifting for us, and a world in which we want to place our models. We might be tempted to just place as many objects as possible to create rich and huge world, since we already have models so well optimized. But there's a limit to everything, and both CPU and GPU are not limitless, and above some threshold, the game will just be lagging. No one likes that. That is why, apart from using a common sense, there are a few tricks that game developers use. Each of them deserve a dedicated video, to be honest. For now, however, I will just briefly mention them. First method is to use LODs. level of details, which are basically the alternate version of our models. So if we look at the model up close, it would be at its full resolution, but the further away it goes, the less detail, so less points it would have. Same goes for textures. The further away we are, the smaller the textures can be. As, let's get real, from this distance, it could really just be 4 points and 16 pixel color texture. We could also just not show it at all, which is yet another method called distance culling. This basically means to just not show objects that are really far away. We can occlude objects, which means we check if something is in front of them, and if that's the case, we do not process it further on. And there is also frustum culling, which is a fancy name to remove everything that is not in camera view, for example, behind the player. There are obviously more methods to deal with big words, but those are the most popular ones, I think. Need more info on any of them? Let me know in comments. So we have a word, we have objects with LODs, and some cool optimizations in code. But the word would either look like this, which is not something we expect from 3D games, or like this. Why? Because we need light. Adding a sun means basically having a huge flashlight pointed in one direction with infinite bounds. Infinite in order to lighten up the whole virtual world, obviously. This allows us to calculate how the whole scene would look like, so the world is no longer flat. I mean, you can stylize it to fake 2D look, but you still create lights and shadows to add depth. Obviously, sun is not the only light that is added to the scene, as you might have lamps, fireplaces, or just some spooky areas. There are two major types of light: casting shadows and not casting shadows. The ones not casting shadows are relatively light, as they basically just add color or brightness in the chosen area. But the ones casting shadows can really mess up the game performance, as they need to calculate shadows, obviously. In order to do so, they create something called shadow map, which I will not be explaining very deeply in this video. What you need to know for now is that every light source that casts shadow needs to create a dedicated image, which is then translated to actual lights and shadows that we see from player's perspective on a screen. The more such lights in the scene, the more shadow maps have to be created in real time and then merged together, and this is all very expensive performance-wise. There is a trick for that, obviously, which is called light baking. Depending on a game engine or programmer's approach, it is either creating those images, shadow maps, offline, not real time, or the opposite can be created, a light map. Light map is basically additional texture that you glue to the model with hard-coded information where the object is in light and where it is in shadow. Both approaches can be successfully done, however, only for static lights and only for static objects. Why? Because without calculating lights and shadows in real time, the shadows will still be there if you destroy the light or an object, and it just looks stupid. It doesn't mean games don't have dynamic lights with casting shadows, it just means they need to be super cautious of how many lights are visible at the same time in a scene. That's a lot of information, and we only scratched the surface. Because now, when we have all this, we can actually play the game and see it on screen. But wait, how? This is a 3D world, and this is just a flat screen. Nice catch! This is when rendering pipeline comes in on a white stallion. For 3D games, the whole rendering pipeline is a complex but efficient way to convert 3D world that exists virtually in-game into a 2D screen. So, technically, anything you see is just a flat image, even though it does fake 3 dimensions perfectly. I will create a whole video dedicated to this topic, or if I already created it, the link is in the description. Now I will just say this. Smart people figured how to translate this 3D world with all its points and all its textures and all its information into 2D screen. It's done in a few steps, during which, first, we calculate the position of each point of a model on a screen, and 3 points create triangles, as we already discussed. We keep in mind the perspective and the view bounds, and we clip out anything that is not in camera view. Then we rasterize those triangles, which is basically figuring out which pixels of your screen are connected to which triangle of a word. We color those pixels based on information sent from the original points and textures, which basically means to create an image by filling the pixels with desired colors. This is also the moment when we decide if the pixel should be visible based on something called the buffer, which basically is black and white visualization of how far from camera the closest object is. The further to camera it is, the whiter the buffer, and this way GPU knows not to show pixels that are assigned to geometries occluded by something else. The whole process is much more complex, but for now, it's enough to understand the importance of points, triangles, and translating from 3 dimensions to 2 dimensions. But again, more details will be in the next video. Those 3 main steps happen for every piece of geometry until the whole screen is rendered image. So the more objects there is, the more work has to be done. And we have only 1 frame for it, which is around 33 milliseconds for 30 FPS games or 16 milliseconds for 60 FPS games. So there is not much time for calculations, as you can see. And calculating game scene onto the screen is really not the only thing that happens during this frame, even though I do focus on it now. All of those steps require CPU and GPU exchanging information between each other constantly. Depending on a rendering type, forward or deferred, we calculate light at a different stage. I will cover the differences between them in a separate video as this one is already too long. Of course, I simplified it all, as we also have things like aerial perspective, FXs, maybe some volumetric effects, so you know it's just an introductory video, don't shoot me. It's also often not the end of the work, as we might want to add post-processes. What are those? They are exactly this. Processes happen in post everything else. Those are effects added uniformly to the whole screen when we already have everything rendered. In other words, if we have this image created after rendering pipeline, we might want to color it blue. This wouldn't be too sophisticated, but it is technically post-process. But why stop here? Instead of blue, let's add gradient. Let's add rain that shows raindrops all over the place, and another effect that creates bokeh on camera. And now let's stylize it with toon shader we all know and love. Each of those effects alter the original image and make it look cool, or you know, cooler. I cannot really do it that well. Okay, so now we have our scene for just 1 frame. And the player just moved a mouse and turned a camera around, so we need to do it all again. And again. And that's it. I really hope I brought some light and some smile to your day and that you had fun learning fundamental knowledge about 3D graphics rendered in real time. If there's anything else you would like me to cover, let me know in comments. That's it for today. You know the drill. Don't like, don't subscribe, and I see ya when I see ya. Pa-pa!